to this great conference in this wonderful location. So it's such a great pleasure to be here in Natal. I already had a great swim in the morning with crazy waves and at the dunes for that matter. So quantum at the dunes. Those of you who heard me speak recently mostly encountered talks of a rather practical nature on quantum algorithms, quantum advantages, fault tolerance, and quantum error correction. But these talks here are relatively short, so I thought it would work better if I put a simple, single, foundational, and hopefully compelling question into the center of all this when we're concerned with quantum chaos without chaos, an operational perspective to entanglement, magic, and quantum chaos. And the single simple question is, what can a computationally bounded observer, so anybody who can resort to computationally and sample efficient protocols, aka you and me, actually do and observe? Well, you say, wait a minute, how can this give a talk? I mean, isn't that what we always assume, that everything we do has to be efficient in one way or the other? Well, we'll see, and we will have a look at this question in 2.5 readings. And in the first incarnation, we look at what happens to good old entanglement theory if computational complexity restrictions are actually respected. In the second reading, we say, how can we operationally detect quantum chaos, and what do information and computational complexity have to do with it? And depending on how it goes with time or how tough the chairman is, we might have a bit of an outlook on magic, hypothesis testing, and science lemma for Fernando, who's unfortunately not here today, and the beginning of a program that I'm personally excited about. But let's get going on entanglement and computational complexity. But let's start at the very beginning and think of what a computationally bounded observer actually is. So given two quantum systems that differ in some physical characteristic, in their color, their smell, their texture, and you aim at distinguishing them, what do you do? Well, you look at them, you smell, whatever, and then you judge. Yeah, but what happens if the time required to do so is on par with the age of the universe? In what sense can we then speak about C being a proper, genuine attribute that you can assign to the system? So let's take this as a preliminary definition of a computationally bounded observer. That's one that takes measurements and is operating for a reasonable amount of time. So I'm in a computationally bounded observer. It is what it is. You are also. Life is finite. I had to break it. So let's make it a test. Okay? Here's one. Here's a picture. And you have to judge whether the boxes are the same or different. Now, who thinks they're the same? Who thinks they're different? Okay. Most people think they're the same, but they're not. They're slightly different. It's a bit hidden there. I gave you a finite time, fine. It's not so easy, but, well, it's not so easy to check anyway, but this is like one instance. In proper problems, we should look at families of instances that are like governed by some sort of scale we would call a problem, where n is the problem size, or an algorithm with time t, efficient if the time it runs to come to a conclusion, if that's polynomial, it's efficient, and it would be called inefficient if this requires super polynomial time. So, in this spirit, what is pseudo-entanglement? That's a kind of fun thing. It's about states, or rather pairs of families of states. One family has the property that if you look at cuts over this many-body state, most cuts will give rise to a value that's close to maximally entangled, and the other one has the property that if you look at the cuts, it will be close to logarithmically entangled, hardly any entanglement. And you want to see which one is which. You say, oh, wait, it's very different. Maximum entangled, almost not entangled whatsoever. But these are there's examples of pairs of such states that are built on certain subsets, on pseudo-random functions, so cryptographic primitives that are functions that look like uniformly distributed in a precise sense for computationally bounded algorithms. states where one is close to maximally entangled, the other one is logarithmically entangled, but from polymany samples, you cannot distinguish which one is which. Okay? This is interesting, but can you make this kind of more operational? What operational consequences does that have in the good old LUCC asymptotic entanglement manipulation setting? And the father, the mother, the I don't know what, diverse of all statements of this kind is this famous mid-90s Bennett result on entanglement manipulation. Everybody is doing a course, and quantum information has put this into the center of things. Yeah, Tony, you published about this already in, I don't know how many years ago. So one of the biggest statements here is that the entanglement entropy, the one entanglement entropy is the one number to rule them all, in the sense that if you look at asymptotic entanglement manipulation, you have a number of copies of states, you can make maximal entangled states out of them asymptotically perfectly at the rate given by the one entanglement entropy. You can come back to another state with a rate that's governed by the one entropy. You can come back to maximum entanglement, to yet other ones. There's one number that says everything about asymptotic entanglement manipulation, and this gives rise to asymptotic reversibility of pure state entanglement manipulation. This is like 90s result of this one number, the one entropy governs it all. And then we thought, wait, are the operations you do actually efficient? Because communication makes little sense if you think about computational inefficient settings. And we were extremely surprised, or our head was blowing away when we realized that's actually not the case. And if you look at efficient operations, computationally bounded observers, things are getting quite different. And there are families of states with computational entanglement distillation that is governed by the min entropy, the infinite entropy, like the single shot quantity, whereas the cost is actually linear, it's almost maximum. So the min entropy is the right thing. In other words, the mother of all entanglement statements in entanglement theory is actually not quite, is missing the point, in that if you do efficient operations that you can do, life is finite, that's all we have, the entanglement entropy is not the right quantity, but it should rather be replaced by the min entropy and not the one entropy. I was astounded. I mean, how is this possible? I don't know. Maybe this is a bit of, there's 30 years of entanglement theory and 30 years of quantum computing theory. I can only suspect that maybe these groups didn't talk enough over the years. I find it funny that the operations you do in entanglement theory are not efficient operations. You don't have to be surprised. I was surprised. And I did my PhD on this. Good. Simulating quantum chaos without chaos. Now we get more physicsy. And if you get physicsy, you have to talk about Hamiltonians. You must have encountered this when you give physics talks and there's not a Hamiltonian, people get very angry at you. You know this, right? No, we don't know the Hamiltonian. It's an unknown Hamiltonian. But there is a Hamiltonian. I give special credit to Lorenzo here. And you have to say, what does it mean to distinguish Hamiltonians? Okay, you can't look at them. They're unknown. So we have to look at how to do things in labs, or in more computer science speak, what's the oracle axis we have. So I go into the lab. That was, of course, a joke. I mean, never let a theorist into the lab, but somebody else goes into somebody else's lab and you take data and then you look at it. What happens? That's what you do. Here, Ulrich does that. He goes to the lab, looks at data. Data is all we have. So what is common is you take a Hamiltonian, or a system, you let it go in time. That's time evolution. It's black box access to Hamiltonian. That doesn't mean time evolution. That's very common for reasonable times. So polynomial times. Life is polynomial too. So take, please, time that's polynomial. And there's access to Gibbs states for reasonable temperatures that are, in a precise sense, also efficient. That's what you can do. You look at systems in time, or you have thermal states. At least that's what we take for granted for the rest of this main part of this stuff. So what does it mean to be computationally indistinguishable? So two ensembles of Hamiltonians are computationally indistinguishable if no efficient algorithm, so with polymany steps, finite lifetime, don't forget, you can discriminate, give one from the other with black box Hamiltonian from one or the other, and you have polymany of them. Polymany preparations, labs, run times, with time evolution, Gibbs state, you combine this, that's what you have. It's very meaningful. It looks fanciful. It's not fanciful. You go into labs, you take data. And then you say, what is quantum chaos? I didn't say this. That's delicate. Because quantum chaos has a long tradition. There's conference on this. It's a bit subtle because we know what deterministic chaos is in classical physics. In quantum physics, it's a bit funny. Yeah, there's a big conference on this. It gets usually heated. There's lots of arguments. It's also in condensed matter, so people are a bit more aggressive. The last time I was at a conference on this, there was somebody giving a talk. It's not a stellar talk, but it was okay. And then there was this question afterwards. I disagree with everything you say. We lost half hour. So, whoa. Anyway, so it's a bit heated. But the trouble is, of course, that it's complicated, right? I mean, the immediate translation of the butterfly effect in classical physics doesn't elevate to the quantum setting because scalar products are preserved under time. Well, surprise, surprise. And there's also naturally 2 to the power of n constant motion, even just the overlaps with the many-body eigenstates. So the original jargon doesn't immediately carry over. But of course, you can do lots of things. People think about level statistics and say a quantum system would be quantum chaotic if the level spacing would resemble that of a classical chaotic system. You could think of semi-classical approaches or decoherence open systems, one where you say, I have an open system and there's like emergent patterns in Wigner functions that look like the classical chaotic one. Or you think of reactions to perturbations, you do something here and you react. So there's a big literature on what quantum chaos ultimately is at the end of the day. Okay, maybe I put questions at the end, but your question I will answer. I will say something about that. That's a certain, I answer your question. When I come to this, I will mention you. In fact, I will do this now. Okay, so here, that's the thing. That's a very common thing. I mean, in many-body physics, that's one of the big mysteries. You take the eigenvalues of the many-body eigenstates, you order them, and look at the distribution of level spacings along the way. And there's very characteristic scalings that you have for generic systems that don't depend on the microscopics of the system so much. And in fact, for Wigner-Dyson statistics, you have like the property that the distribution goes to 0 at 0, which means there's a level repulsion. They don't, statistically speaking, they don't like each other and go away from each other. Whereas for integrable systems, you expect Poisson statistics, which means that where you see the distribution. That's a generally valid thing. You have to be careful. They are not mathematical theorems. You can construct counterexamples. I've done lots of them in my own past, but on condensed matter jargon, you put systems usually into these boxes. I think that's a fair statement. Have I answered your question? Very good. There's also a bit of a shift of emphasis in that people are more and more shifting the emphasis to emergent properties of unitary dynamics to capture quantum chaos. And they say, well, I don't want to say what quantum chaos is, but I say a system is quantum chaotic if it shows features of a chaotic system. And if it features chaotic dynamics of a kind. Yeah, that's not such a bad thing. So what people usually agree on is that quantum chaos is nicely captured by an ensemble, the so-called Gaussian unitary ensemble. You can make it a test. You can pick 10 identically prepared condensed matter physicists and ask them whether they like the GOE as a way of capturing quantum chaos. Most likely they will say yes. I've done this experiment on my corridor. It has worked. So jokes aside, this is a very common minimum consensus that what quantum chaos, whatever is that's captured by the Gaussian unitary ensemble. And what is that? Hamiltonian is always a Hermitian matrix, can be written as U, D, U dagger. U is H random, and D is a diagonal matrix with the right level spacing. Again, coming to your thing, it has the right level spacing that comes here. It's even spelled out. That is the one that is expected from quantum chaotic dynamics. And that's, you see this right level repulsion that we've already discussed. That's what people usually take as the ensemble of quantum chaos. And then they say what follows from that and what properties do you see. These slides are a little bit full, but the message is very clear. So what people usually do when they want to capture chaotic dynamics, they think about the response, what happens if you do something with it. Say you have a local operator, and then you see what happens to this guy in the Heisenberg picture in time. It kind of spreads out. And one common measure is the scrambling measured by a test operator O2 via the decay of the so-called out-of-time ordered correlation function that recently in quantum info rose to fame because Google made this relatively loud claim of a quantum advantage based on OTOCs, out-of-time ordered correlation functions, which are not so easy to simulate, and they're expected to decay in n like exponential way in chaotic systems. You can think of scrambling measured by the operator entanglement that you all know and love. So you take your state, you vectorize it, and then think of like entanglement in the choice state, so to say, that is generated by the chaotic dynamics with a certain characteristic in this entanglement entropy. If you think of chaotic dynamics, that this would be omega n, again as an observable feature of a kind. Or take long-time dynamics. States are, for quantum chaos, expected to be complex and far from being classically simulatable. If you let them go in time, then chaotic evolution would produce very entangled states at long times. Again, when they're chaotic, you would expect this to be order n, so they spread all over the place, and it would be close to being maximum. So, again, this Gaussian unitary ensemble that we have already agreed on, that people agree on, is paradigmatically fulfilling all those chaotic properties. It's not so difficult to see that you see that it's fulfilling that. That's good to know, because otherwise it would be not consistent. So people move to chaos as like probes to chaos. Maybe they're not necessary, but sufficient. So the modern approach to chaos is to detect chaos from emergent physical properties. They look at 4-point out-of-time ordered correlation functions, Raynier entropies, operator entanglement, stabilizer entropy, and so whatever. So if a system looks like quantum chaotic, it is quantum chaotic. If an animal looks like a dog, it is like a dog. That's the reasoning. It's not so bad. So, good. 60 minutes into the talk. I will also keep up with time. I don't overrun. So I come to the key point in a second. Good. But then we have to put the observer into the focus. That's what I said at the beginning. We are computationally bounded. What can we do with our eyes, with our finite lifetime? What can a computationally bounded observer see and do? So here we push the role of the computationally bounded observer in. So is the following possible? That looks fanciful. It's not. So given an ensemble of chaotic Hamiltonians, there's two things. One is an ensemble of chaotic Hamiltonians, which obeys all the necessary properties of quantum chaos. All the ones I listed before. OTOCs, long-time evolution, scrambling, operator entanglement, all that. A quantum chaotic one of pseudo-chaotic Hamiltonians. And there's another one. This is the chaotic one. There's another one here that has none of these properties. It's just not chaotic in any of the senses. It has the wrong long-time evolution. It has the wrong OTOCs. Not only has the wrong level spacing, it has no level spacing whatsoever. It's just not quantum chaotic. And this I spelled out. Okay, here we go. It does not exhibit the chaotic properties, no level repulsion, weak scrambling, low level entanglement. It's just not true in any of the mentioned senses. Okay, not chaotic. Chaotic. With the property that it's indistinguishable by any computation efficient algorithm with Hamiltonian access. You look at it, you take data throughout your life, you take it, you reason with your supercomputer for 10 years, and you cannot discriminate the chaotic one from the not chaotic one. What? Wait, I mean, how is this possible? It cannot exist. Because if it existed, all so-called necessary probes of quantum chaos lead to the same emergent phenomena. If I have a quantum chaotic system here and one that's wrong in all possible aspects, and I cannot discriminate them, I mean, what's left? But it does exist. And I give you, because I want to keep time, I give you the high-level argument of the proof. It's long and winding. It's a glossy paper with like 40 pages of lemmas and propositions in the appendix. The upshot is that the eigenstates are called pseudo-random states, or efficiently preparable proxies of high-random states. And the distributions are on the single marginal level, ones that follow this Wigner semicircle law, so correct on the marginal level. And then you look at the product. Uncorrelated, no level spacing. You just product it up from the right single marginal Wigner semicircle law. That's the construction, and then the misery and pain follows through the proof. So we spoof eigenvectors and eigenvectors separately, and the one ensemble is computationally not discriminatable from the GOE given black box Hamiltonian axis or time evolution and final temperature evolution. Okay, so here's a summary. So here's the two settings. One is a pseudo GOE that has no level repulsion. The other one has level repulsion. Then autocs are saturating at totally the wrong levels. Say, okay, well then why don't I look at them? Well, they're saturated at the wrong levels, but your life is over before. It takes too long. The asymptotics is wrong, but you don't see it. Or weakly entangled states, you got weakly entangled states and highly entangled states, but from polymeric samples, you cannot discriminate one from the other. So you must be joking, but that's what it is. This has a number of, so you cannot computationally discriminate one from the other. This has a number of applications and implications. One thing is that you can actually efficiently simulate one. The spoofed one is efficiently implementable on a quantum computer, while the GOE cannot, with poly-sample gate complexity, be simulated. It's a simulatable version of the other. It also shows that there's no experimental way of detecting Wigner-Dyson versus Poisson, because there would be an immediate contradiction with our theorem. That's a very physicsy notion. You cannot, with efficient tools, check it. It's a corollary of our statement. Also, as a technical corollary, it gives a sample complexity lower bound for scramble properties of autocs, again, that are like timely for the mentioned Google results along these ways. So, what does that all mean? And the honest answer is, I don't quite know. It's a theorem, judge for yourself. It's a bit funny. It's like you say, I look at the sky, and what's the color of the sky? You look at this with polytime, you take data, you think about this for polynomial time, and you try to draw conclusions. But from polymany data, you cannot judge whether the sky is blue or red. Then what does it mean, ontologically speaking, to say that the sky is blue, if you cannot judge it from polymany data? I find that compelling. I mean, I give you the theorem, you make something with it. Coda, I just summarize, and then I'm in with my time because I want to leave some time for questions. So in this talk, we looked at computation-bounded observers, which is a ridiculously reasonable assumption, which is just saying all you ever do has to be computationally and sample efficient. I mean, it's in quantum computing, it's the mantra number one. In other settings, it's not so common, strangely uncommon, to my understanding. And we looked at consequences thereof. We found a number of interesting and I find also somewhat irritating consequences. I should say that this is for us, not the end, but rather the beginning of the program. So we thought about physics incarnation, now we look at coherence as a paper coming up, on thermalization as a paper coming up, but it also has interesting consequences in quantum information theory, where we think about hypothesis testing and Stein's lemma under computational constraints, and that puts everything upside down. If Fernando had been here, I would have been saying something about this. Stein's lemma is very different under computation-bounded observers. Or you get like things like channel capacities. Here, Dagmar is here. Good old questions that we did in the 0 years. There's channels which have a positive quantum capacity. You can get qubits across at a positive rate. But the computationally bounded capacity is 0. It's a bound capacity. Because communication is ridiculous if you allow for exponential resources. Then I make a box with all the messages in, I give you the label. Think about this. So if you're computation bounded, there's channel capacities which are 0, but the old style capacity is not 0. It's actually close to maximum. And there's a paper that came out just not long ago. Or magic. There's states that look magic, but they're not in the same sense. That's pseudo magic, and this is an interesting concept in a way. This paper came out last Friday that I'm very happy about. Also, deciding on magic is hard, computationally hard in a precise sense. So again, there's kind of physicsy and computer sciencey question coming in, which is like strange because it's a polytope. How can a weak membership problem of a polytope be hard? Well, that's what we look at in this. Oh, 24 minutes 40, very good. That brings me to the last slide. So in this talk, I try to be provocative and say, I make a super basic assumption. As I say, everything you do is finite, it's poly. What conclusions can you draw from that? And we had a number of things. We thought entanglement theory has to be rewritten to an extent. Chaos is getting funny, but there's also other settings, other consequences in a way. So the paradigm we advocate is that of computationally bounded observers. And for physics, that's introducing a new perspective because the observer now is not just a guy outside or a woman outside, but it's the verifier. It's not a verifier, but it's an integral part of the theory itself. Because in what way can you speak about physics if discriminating one property from the other is not efficiently possible? In what way can you then speak of properties of physical systems that you encounter? And that's more like a question that I throw into the audience. And on this note, I thank you so very much for your attention, and I'm looking forward to questions you might possibly have. Thank you very much indeed.
Questions? Questions? You're closer.
Sorry.
So one corollary of what you said is that these resources, for example, if I have a state that has magic, but it's a magic that is not distinguishable from pseudo magic with this computational bound, like, does this imply that this resource is going to be useless for computational advantage?
Okay, the short answer is yes, I would think so. And I think it's subtle. I mean, even the last paper I mentioned here makes a kind of similar point. I mean, you can say that there's the classical world and the quantum world. The classical world is like classical efficient simulator, we'll say, with Pauli propagation methods, and then the quantum side has magic, and then that's the realm where you can think of quantum advantages of quantum algorithms. So there's a line in the middle. Finally, the line is kind of hard. And then you talk to come up to your question. You talk to practitioners in quantum error correction here. There's the Jülich gang here. And you say, oh, there's one of the canonical way of think of universal fault-tolerant computing is like doing transversal Clifford gates and then making that universal with magic state distillation. Common resource is the T magic, the T resource, and you distill it and teleport that in, and then you make a fault-tolerant universal circuit. But then you say, oh, I take a CZZ magic resource, or another one. Why would I not use another one that is useful? But I say, oh, it's hard to decide, you cannot judge. But then I would come to your point, yeah, I would say if you cannot judge, it's kind of practically useless, because if you could, you would not know how to use it. So for finite lives, yeah, I agree, it's useless. I mean, practically.
Question?
Thank you for your talk. Can you make any assessment about those sets of Hamiltonians that are not chaotic, but that we cannot easily distinguish from chaotic Hamiltonians? Are they easy to be found in nature?
That's a wonderful question. And that's a wonderful question. And in a way, this is, I defend my position, but it's kind of the weakest link of our work in a way, because you're basically asking the question of how reasonable are these Hamiltonians? And we are following, because our Hamiltonians are not quite local, for example. And you say, how easy are they? I mean, they're efficiently preparable. So, I mean, to answer your question, yes, they're all efficiently preparable. Answered your question. But I have more to say, which is how physically natural are they? We are now following up on making them more local, for example. And that's a reasonable scientific thing. It gives a good paper. Yeah. But then I would also defend our point that it's not so much about how reasonable the Hamiltonians are, but it's about the judgment you can do from data. I look at data, what is a natural inference from those data about a physical system and about a property you have? So for that, the Hamiltonian you argue about does not have to be so physically meaningful, because all we say is that that conclusion is not valid. You see? We can discuss that also later. I even have an anecdote for this, but maybe it's not the right time to talk about anecdotes.
Okay, more questions? have a short one regarding the part about this pseudo chaotic Hamiltonians. What is that you prove exactly that the amount of time that you need to have it switch it on in order to distinguish the two classes is really large, no? But independently of the measurements independent of the operations or the complexity of the
That's
operation.
correct.
Okay.
So
it's a very strong result. There's no stronger than computational result, no?
That's a hard. That's right. So the long-term asymptotic is actually quite different. It's not small, but it's a vast difference. But we couldn't even make a plot. We looked at this. They look very similar for long times, but then they look different. But then you cannot wait for so long. That's precisely right. It looks similar for many times, and then it goes further. So, maybe I can say this because a friend of mine gave a similar talk some time ago, and then it was well received. It was a wonderful talk. But then more condensed matter trained people came and said, "Yeah, great, but what's your Hamiltonian?" I said, "Well, there's no Hamiltonian. I'm talking about what conclusions you can draw from data about physical properties. But there must be a Hamiltonian. Show it." I said, "Well, that's not the point. Of course, I would write a Hamiltonian, but it's not the point of my. There must be a Hamiltonian. For physicists, it's a bit of a hard sell because they usually do physics this way around. You make a model, and then you make assumptions, and you make a plot. And if the plot looks kind of similar to the thing you see in nature, you say, that's the right theory. But it's not so common to the reverse. You take data and say, from data, I conclude things. It's like, is David in the audience? I don't know. It's like more the tomographic viewpoint of physics. You take data, you say, what is a legitimate conclusion from data, which is it's a good way of doing physics, because that is how it should be, I think. Yes, thank you. Oh. On that note, thank you very much.
Again.